Hello again, my dear students. Now this is the final and the fifth part for our first lecture related to the Fourier transform and the frequency domain analysis. If you remember, in the previous part, we have reached this important slide dealing with the relation between convolution and multiplication in the time and frequency domain. And as you can see, as a summary in this slide, we have concluded that whenever you have a system with an input x of t and an output y of t with a system time response h of t, the relation in the time domain will be given is y of t equals to h of t times x of t. Y of t equals h of t convoluted with x of t. So this relation can be transferred in the frequency domain to be y of omega equals to h of omega times x of omega. So multiplication in the frequency domain is converted to convolution in the time domain. Now we are going to solve a new example that may be important for us to understand the importance, the level of importance with dealing with the Fourier transform and the convolution theory, and how we can reach some important observations related to the system performance. The example is as follows. Now we have a system with a time response h of t given by 1 over rc e power minus t over rc u of t, where u is a unit step function. And we have a rect function considered as an input function. What we are interested in to get y of t. Now, in order to solve such a problem, you have actually two ways, two perspectives. Either to solve it from a time domain perspective, considering the convolution between h of t and x of t, or to consider it from the frequency domain perspective by multiplicating h of omega and x of omega. So you have first to make a Fourier transform of h of t to get h of omega, which is the system frequency response, and also we have to do the same for x of t to get x of omega to get the input frequency spectrum. So this is what we shall do. What I'm going to do in this part is that I'm going to solve this problem from a frequency perspective. Herein, I am seeking for your encouragement, your motivation, in order to resolve this problem from the time domain perspective by doing a convolution, and then we can check the validity of the both answers. So, in order to proceed with this solution, now I have to turn to my simple whiteboard screen, and also I will start step-by-step solving this equation. So please now permit me to use my white screen, stop sharing the presentation, and start doing the step-by-step solution. Okay, so let's first start to understand the nature of the input signal and the time response signal. Let's start with the time response of the system, which is h of t. H of t is given as 1 over rc e power minus t over rc times u of t. As you can see, it's an amplitude, a negatively decaying exponential ionic step function. In order to understand this equation, or in order to understand this signal, we have first to try to plot it in the time domain as a first step. So what we are going to do now is as follows. First, let's plot this negative exponential. So this is the time axis, and now I'm going to plot e power minus t over rc. As you can see in this graph, when t is equal to 0, we have e power 0, which is 1. Whenever t starts to increase, we will have a negative decaying exponential. When t reaches infinity, then we have e power negative infinity, which is 0. So we have a negatively decaying exponential. And this exponential actually is going here upward like that. So this is the e power minus or e power negative t RC signal.
So this is the negatively exponential decaying function. So what about the unit step function? If you remember from your signal classes, now we have a u of t function in this manner. It's 0 where t is smaller than 0 and it's equal to 1 whenever t is greater than 1. This is the standard unit step function as you know. So by multiplying these two functions together, we get, and of course now we have an amplitude 1 over RC, so we will have something like that. Now this is the maximum value, which is 1 over RC, because 1 multiplied by 1 over RC, it will have 1 over RC, and then this e power minus t over RC. And for t smaller than 0, the output is 0 because simply the function is 0. So this is the time response for our system. Now we are interested to get what's called the h of omega. The h of omega, as we know, is simply obtained by having a Fourier transform for the h of t function, which is the time response function of the system. So this is our next step. Now we are interested to have the h of omega. We know that h of omega is equals to integration from negative infinity to infinity for h of t e power minus j omega t dt. So very simple. As we have a unit step function, this integration will be limited only from 0 to infinity, not from negative infinity to infinity. And then we have our function in this manner. So we will say h of omega equals to integration from 0 to infinity for our function, which is 1 over RC e power minus t over RC times e power minus j omega t dt. Here, 1 over RC, of course, is a constant with respect to the integration, which is integration with respect to time. So we have to get it outside the integration. And then this is the integration from 0 to infinity. E power minus t over RC, e power minus j omega t. So simply this is e power minus 1 over RC plus j omega all t dt. Again, remember the rule for integration in case we have an exponential. So a very simple equation. So 1 over RC is here the denominator, and then we get all the coefficients of the exponential term in the denominator. So we have a minus sign here, and we have 1 over RC plus j omega. And then we have that term here, e power minus 1 over RC plus j omega t, and the limits of integration are from 0 to infinity. By substitution here, my dear students, then we have negative 1 over RC again, and we have 1 over RC plus j omega, and here we have e power negative infinity. E power negative infinity is equals to 1 equals to 0, sorry, and then minus e power 0, which is equals to 1. So again, negative with negative, then you will get that h of omega is equals to 1 over RC over 1 over RC plus j omega. If you have a good memory, you will recognize that this is simply the first example we solved it together when we have a resistance and a capacitor. And you remember that for this example, we have plotted the h of omega as an absolute h of omega, if you remember, because we say this is a complex function, so we have to plot the absolute and the phase. So the absolute of x of omega, which is simply, if you remember, it was something like that, 1 over RC over the square root of 1 over RC square plus omega square. And we say that for omega equals to 0, we will have an output equals to 1, and then we have something like that, and we call this, if you remember, a low pass filter. So this is simply the h of omega we have now. This represents the frequency response of our system, which is simply a low pass filter. So this is the first part of the process. We have now converted h of t into h of omega. The second part is that we have also to convert the input x of t to the frequency domain to get x of omega. So as given in the head of the question, x of t is defined as rect t. So very simply, it's a rect function with one amplitude and with one here as a function. So this problem already has been solved before. If you remember, my dear students, it's now extended from negative zero point 0.5 to zero point 0.5. So it's very simple way. It's a very simple way of having a Fourier transform, because this is simply at x of omega is simply the integration from negative zero point 0.5 to zero point 0.5 for just e power minus j omega t dt, because simply here the magnitude is 1, which is the right function magnitude. Accordingly, we will have the function negative 1 over j omega, and here we will have the e power minus j omega t extended from zero point 0.5, negative zero point 0.5 to zero point 0.5. This is just some sort of revision. We already know the output, which is the same function. So negative 1 over j omega, and here we have e power minus j omega over 2. This is the zero point 0.5 minus e power j omega over 2. Now we can enter this negative sign inside the bracket, so we can switch the two terms, and also we can have 2j here in order to get the sinusoidal expression, if you remember. So it will turn that x of omega is equals to 2 over omega sine omega over 2. I think so. That's all. So this is the expression for the this is the expression for the sinusoidal signal. Of course, if you remember, if we pick up, or if we convert this omega into 2 pi f, we will reach the same expression. But here we have, or here we use the term omega as our reference, not f. That's why I will keep it in this way. However, of course, both mathematically have the same definition, or the same meaning mathematically. We can now also start to plot this function, by the way. So we can say that this is the f-axis, or I'm sorry, this is the omega axis, and this is x of omega axis. So you can say, of course, we already have tackled this before. So when it's 0, you will say that this is a 0 over 0. Then we will make a limit, and as an output for the limit, we will have a value of 1 here, if you remember, by doing a differentiation for the denominator and the denominator, and also for the other side. Yeah, then you can check whenever this signal will reach 0. you will find that this signal will reach 0 when omega over 2 is simply equals to multiples of pi, which is n pi, where pi is not equal 0 and pi, sorry, n is not equal 0 and n equal 1, 2, 3, 4, blah, blah, blah. So for omega equals to simply 2n pi, we will have such a plus or minus. So simply you will find something like that in this manner, where here this is n equal 1, so this is 2 pi, and then this is 3 pi, and then this is 4 pi, and so on. If you would like to plot also the magnitude of or the absolute value of x of omega, it will be simply turn to be a first quad signal, so it will be something like that, and so on. So this is simply x of omega. Now we have an x of omega, we have the h of omega. What we are going simply to do is that we are going to just multiply both signals together. So now our output, which is y of omega, is simply the multiplication of h of omega times x of omega. Then here h of omega, if you remember from my previous slide, 2 slides actually ago, we have already defined h of omega as 1 over RC over 1 over RC j omega. So 1 over RC times or 1 over RC times 1 over 1 over RC plus j omega. This is the h of omega times x of omega, which is simply omega over 2 times sine omega over 2. So we can make it in a better mathematical manner and say it's omega over 2RC times sine omega over 2 over 1 over R plus j omega. This is a very simple 1 over R, I'm sorry, 1 over R. Okay. This is a very simple manner. But what is also interesting is to make this in the terms of graphical representation. What I mean here is as follows. We know the term x of omega. So this is omega. So we know the term of x of omega, which is something like that. And also we know the term or the function h of omega. Again, here I'm plotting the absolute values for these complex functions, so which is something like that. As I previously mentioned, the y of omega is simply the multiplication of this structure or these signals together. So for zero frequency component of x of omega, this x of omega will directly be multiplied with nearly 1 or absolutely 1 when we are talking about the zero frequency. Whenever, while for higher component of frequency, here I mean the x higher component, this function will attenuate it till it reaches 0. That's why we are calling this as some sort of low pass filter, because we are getting rid from what we can call the frequency, what we are getting rid from what we can call a frequency, or what we can call a zero, sorry, what we can call a high frequency component. So a very simple manner. This is a filter. This is a low pass filter. So all these high frequency components will be get rid. So by the end of the day, we will have something like that. So we get rid from these high frequency components. We only bought the low frequency. Now, in order to get the term y of t, in order to get the term y of t, we have now to think to some extent. Mathematically, we are able to get the term y of t because y of t is simply the inverse Fourier transform for these functions. Maybe it is somehow complicated from a mathematical manner, but it's doable. You can just insert this function into the inverse Fourier transform equation, and then you can get the inverse the y of t function. So this is y of omega, and simply y of t is simply the uh, inverse Fourier transform for y of omega. Very simple like that. However, before proceeding to, or I'm not going to waste time in doing mathematics here, but I'm just need start to think about concepts. How we should expect the term y of omega. So now we have x of t, which is the input signal. It looks like a rect function. And this rect function passes through what we can call a low-pass filter. So the main function of this low-pass filter is to get rid from high-frequency component. If you remember the beginning of our first lecture, and when we start to demonstrate or flashback some notes about Fourier series, we have a very important observation related to the inclusion of the high frequency component in the short edges. If you remember, we do it in the first part, maybe in this lecture. So these sharp edges represent the high frequency component. So this is the high frequency component. Whenever you get rid from this high frequency component, you should expect a time domain signal in this manner. As you can see, these sharp edges turns to be smooth edges because now you exclude the high frequency component. And that's why we call the low pass filter, we call it a smoothing filter. Because whenever you get rid from these sharp edges, your signal becomes more and more smooth. And that's why it turns in this manner. So maybe without using mathematics, you can expect the output of y of t in a very easy and very simple manner. So now let me return back to my slide, my dear students, and let's see together the output we have got uh, from the presentation. Okay, that's perfect. Let's do now. Okay, I believe now you can see my PowerPoint slides. So let me again use my pointer and start exploring some observation from the example. Actually, this is the example. This is the low pass filter. This is the rect function. And here, this is the output. As you can see, we have this y of t signal. As you can see, or this y of t signal. Here, these are two different outputs with two different 1 over RC. Here, you have to be very, here you have to examine the importance of the 1 over RC parameter. Because simply here, the 1 over RC parameter is a parameter that tune the sharpness of the low pass filter, which frequency component it will cut and which not. This is related to what's called a 3 dB bandwidth. Maybe we can somehow talk about this 3 dB bandwidth later on. So this bandwidth is the bandwidth needed to cut the frequencies. I will show you more examples later on in this presentation. But as you can see, for this more and more tough low pass filter, you nearly or the rect function nearly disappear, as you can see. However, here it still exists. We still see the rect function, but as you can see, no sharp edges exist because you get rid from the high frequency component. Now, this is the frequency domain. This is the h of omega, as we already plotted. We did not plot actually the phase. We plot only the magnitude, as you can see. And also, this is the x of omega, the sync function, usual sync function. And also here we have the output y of omega. As you can see, some high frequency components have disappeared now in this example due to the low pass. So this exactly, especially or this what is it? So here we are talking about the smoothing property of the locus filter. For example, here is a signal. This signal includes a lot of sharp edges in the time domain. Whenever it passes through a locus filter, you can see that now we have a smoothing properties or smoothing features for this signal due to that we get from the high frequency component of the signal. Uh, you can you can filter different types of signals, different types of filtering process depending on whatever you need. Now let's do and let's finalize this by knowing different types of filters. Principally, we have four main types of filters. What I'm plotting here, my dear students, is simply the ideal filter response. What here I'm plotting is what's called the ideal filter response. What I mean by ideal filter response, as you can see here, that we have a very pure, ideal, sharp edge here. Actually, this is a hypothetical example because whenever we see a real locus filter, it looks like that. Here you have a smooth decaying in the frequency domain, it's of omega. But ideally, we plotted like a square wave, like a rect function, like a sharp edge, as you can see here in this example. So this is a very interesting example. For example, for this low pass filter, it's called a low pass filter because, as you can see, this is the omega axis. So for low frequencies from 0 to B, this frequencies of the input signal will pass. However, for any frequency greater than B, which we will call it the cutoff frequency, we will have zero output due to this zero system response. That's why we call this a low pass filter because simply it gets rid from the high frequency component. On the other hand, we call this a high pass filter because simply it only gets rid the low frequency component from 0 to B. Whenever the frequency is greater than B, then these frequencies will pass, so that we call it high frequency component. Again, this is called this is called actually a cutoff frequency, but this is the cutoff frequency for high pass filter. The third type is what's called a band pass filter. Here we are only passing a certain band of frequencies from B1 to B2. This band will only pass from the input signal, otherwise will be zero, as you can see in the left and right. Whenever for the band stop filter, which is actually directly the inverse of this filter, so as you can see here, all frequency will pass except these frequencies from B1 to B2. So these are the main four types of filters that we are going to deal with, or mainly these are globally the four main types of filters. Now, the last question actually we are going to try to answer is how we should determine the cutoff frequency. Here, in a very simple manner, you have a sharp edge that can clear cut the cutoff frequency. So in this low pass filter, for example, you can easily say that whenever the frequency is smaller than B, it will pass. Whenever the frequency is greater than B, it will stop. So it's called a low pass filter. But as I mentioned, in real filters, for example, the first investigated RC filter, it's not that clear. We have a frequency response like that. So we don't have this clear cut, my dear students. So how should we make it? Let me now show you how we should make the bandwidth. Okay, back to my simple whiteboard and then we can start. If you remember, we have already concluded a very simple equation in order to demonstrate a low pass filter, saying that 1 over RC, as you can see here, and again here we have 1 over RC over 1 root 1 over RC all squared plus omega squared. And when we plot this, we come up with something like that. Here, this is omega, and here, this is h of omega. And as you can see, you have something in this manner. So now this amplitude is equals to 1. This is very simple by substitution. substituting with omega equals to 0, you will have 1 over RC over 1 over RC, which is equal to 1. In order to estimate the cutoff frequency, here we have a very important definition, which is called the 3dB bandwidth. The 3dB or the 3 decibel, you know that the decibel is simply 10 log the ratio value. So the 3dB bandwidth actually represents simply 50% of the power. So whenever the response is less than 50%, then you will consider this in the stop band. And whenever it's greater than 50%, you will consider this in the pass band. The maximum value is 1. So 50% of this maximum value is simply 0.5. So what you are going simply to do is to do here a clear cut as this 0.5. And this frequency or this omega will call the cutoff omega. So if omega is smaller than this omega, so this is the pass band. But if it's greater than this omega, then this is the stop band. So you can simply adjust your clear cut by calculating 50% of the maximum value on the frequency response. So this is the simplest way we will usually use in order to estimate the cutoff frequency of any filter. Of course, you can do the same experiment while you are doing with high frequency filters, band pass filters, or band stop filters. All will be implemented with the same manner. Okay, so I believe that technically wise, we have now reached the end of this lecture. I have only one remaining slide, which is actually related to your project, my dear students, which is one of your projects, because we have more than a project to be selected. So this is the image processing in the Fourier group. During our presentation, we deal with the processing of Fourier transformation as the linking, the bridging between the time domain and the frequency domain. So we are converting the frequency into time, or the time into frequency, which is basically correct. However, we have to understand that this is a mathematical tool that is capable to be implemented in different domains. So whenever you are dealing with image processing using a Fourier domain, you are not dealing with a time domain, because here in this image, there is no definition for time. It's actually a static image. So you don't have time in this image. So what you have in this image is not a time. What you have in this image is coordinates. For example, this is the x coordinates and this is the y coordinates. What we call these coordinates is the spatial dimension. The word spatial is extracted from the word space. So when we have spatial dimension, I mean in the x, in the y, in the z, or whatever. So here, the task of Fourier transform is to convert the spatial dimension into the frequency dimension. So that, try to imagine that we are replacing the t by x or by y, where x is the x direction or y is the y direction, which is the spatial domain. So this is another application for Fourier transform, where you are going to do some sort of frequency domain analysis for a spatial domain. Another challenge is the project. This is just a brainstorming. It's your project, so you will do some effort and some research in order to explore more data. I'm just giving you the first push. The second issue is related to the multidimensional Fourier transform, because when we are dealing with time to frequency, so it's a single dimension to single dimension. Time is a single dimension and the frequency is single dimension. See? So it's a direct correlation. However, in this two-dimensional image processing, we are doing a 2D Fourier transform, because you have a two-dimensional image. So we are now interested to convert this two-dimensional
spatial domain into a single dimensional frequency domain, which is another interesting and challenging point, by the way. The third issue is to think about it. What is the information that I can extract from this dummy black or gray image? Why should I convert this two-dimensional graph into two-dimensional spatial graph or photo into a frequency domain? Here you have to think about it. So this is a clue. This is the tips that can push you to search and to seek for more about Fourier transform for image processing. Actually, Fourier transform is used for image processing for a lot of applications, maybe for smoothing, maybe for filtering, maybe actually for compression, by the way. So you can now start searching and start doing your homework maybe in order to progress in your project. Usually we will be following up you to help in MATLAB coding or all this stuff, but of course concepts are left for your side to innovate. Thank you very much, my dear students. This is actually the end, not only for part number 5, this is actually the end for lecture number 1. In lecture number 1, we were dealing with Fourier transform and frequency domain analysis. We know first what is the main difference between dealing with the periodic signals as a Fourier series and dealing with the aperiodic signals as a Fourier transform. Then we do some experiments or some examples, especially this ring sync example with transferring from time domain to frequency domain. After that, we proceed to what's called the Fourier transform properties, where we have shown a lot of properties, but we pick up one property, which is the convolution, where we investigate a lot and we reach what's called the system level, and we study the time response and the frequency response of the system. And again, we did some interesting examples, mathematical examples, in order to study more and more about the system response. And we terminate our lecture with the concept of filters. We know the different 4 types of filter and how we can calculate the cutoff frequency of a filter. This is the termination of the lecture. All the slides, all the handwritten slides will be scanned and will be uploaded for you over the e-learning in addition to the lecture scripts and of course the PowerPoint presentation. And see you with the next lecture, which is the introduction to the analog communication techniques. Thank you very much for your concentration.